Welcome, everyone. Thank you so much for being here. My name is Madeline, and I'm happy to welcome you to this Cohere For AI community talk. Cohere For AI is a research lab looking to change how research is done, where and by whom. And one of the ways we do this is by supporting an international community of machine learning researchers around the world. It's my honor today to introduce to you two of our community members, Jen and Jonas, who have volunteered and taken it upon themselves to organize this wonderful community series. So to get things started, I'll pass things off to Jen to welcome today's speaker.
Great, thank you, Madeline. So it is my absolute pleasure to introduce Catherine Olsson. So Catherine Olsson has had a great career in machine learning. She worked at Google Brain, OpenAI, the Open Philanthropy Project, and now she is at Anthropic AI, whose mission is reliable, interpretable, and steerable AI systems. Catherine also worked on the DOTA project while at OpenAI, which, as I hope many of you know, was able to now be the state-of-the-art DOTA player in the world. And her personal interests are building high-performing, reliable systems by actually understanding how neural nets do what they do. And with that, I'll pass it on to Catherine.
Great. Thanks so much, everyone, for having me. So I'm going to dive in just a moment on getting started in mechanistic interpretability. But before I do that, I would just love if everyone in the chat could just say just a quick sentence about you. I like knowing who the audience is. So please just jump in and type a little something about where you're at or what you're interested in. While you're doing that, I'll just say a little bit more about what we're going to cover today. So I'm going to talk about how to get started in mechanistic interpretability. You might not have heard of this specific subfield of interpretability. So the first thing I will do is kind of warm us up. I'm going to sort of explain what this subfield is and how you can get started in it. Okay, so I'm just going to start jumping in. Feel free to keep dropping information about you there, so I'll sort of see that flowing through. So the overall view of what I'm going to talk about is as following. So first, I want to convince you that mechanistic interpretability is an exciting field, that there's lots of low-hanging fruit. It's approachable to generalists, so to folks like yourselves. And I think there's also some risks of doing this kind of work. So, there's a lot of gotchas and it's kind of a little less legible. So I want to kind of sell both the pros and cons, but I think if you're interested in doing independent ML research, this is a good area to start in. It's growing rapidly. There's a lot to do. So I'll give a bit of an overview from that perspective. So first of all, what is mechanistic interpretability? So I guess I call this audience poll, but I'm going to, again, try and get a little bit of participation here on what is mechanistic interpretability? So if you're able to get a notebook or pull up a little notes, your iCloud notes or something to just think about, I guess I wrote, can we do group shares here? Not quite. So we're not going to do this as a group share. We're going to do a silent write. But so in order to understand what is mechanistic interpretability, I want to introduce us to what are the different types of machine learning interpretability. And I think a given approach to interpreting ML is sort of characterized by these three questions. Who is doing the interpreting? Why do they want to interpret the model? And what type of interpretation will achieve that goal? So I want you all to just do a sort of silent write for a handful of minutes. Just brainstorm three different use cases, three different sets of these three questions. So an example might be I'm a farmer using machine learning as a product for my apple picking, and I want to understand why it's picking the unripe apples. And so I want an explanation. That could be one example. Try and come up with a couple more. So I'll just step back for a few minutes. Okay, I think that's enough time to get some sort of juices flowing and wrap your heads around this question. So I'll just give one example of something I would not call mechanistic interpretability, and then I'll explain what I think counts. So one example that's actually pretty common in the literature is the people interpreting are some kind of end user. Maybe it's doctors who are using some kind of prediction product or system, and they're trying to automatically diagnose liver cancers or something, and they want to look at the diagnosis and be do these outputs of the machine make sense to me, the practitioner, the expert, the end user? And so they want to know in a particular case, why did the model make that judgment? This is not what I'm talking about. this line of work is fantastic. It's important. It's a completely different use case than the type of work that I'm going to be talking about. So I want to distinguish that. I think when people say interpretability, they can mean something like this, which is valuable, and it's a different endeavor. I'm talking about a case where the people interpreting are researchers. There's folks like me. I've also put here my colleague, Nelson Elhaj, who's done a bunch of other fantastic work. So the end users are like highly skilled people. They're you, yourself, with your own eyeballs. It's not about, in this field, making it accessible to some end user or layperson or anything like that. And the reason we're interpreting is we want like a scholarly understanding of what the model learned to do. Our understanding is the thing we publish. It's not some explanation shown in a UI for a user. And the type of explanation we're seeking is like a complete mechanism of the behavior, not a one-sentence summary, not a quick saliency map, but a full account of how the network did what it did. So I'll just pause here if there are any questions about this framework. Okay, cool. So let's jump in. So we're talking about researchers understanding what's really, really going on. So let's just do a quick quiz to test your understanding. So read this abstract and judge, do you think this is mechanistic interpretability? I'll give you a couple seconds and then do a little, I wonder if we can do a hand raise poll. Jonas, is that going to work? You count hands.
Okay, I think it's just going to show just one person.
Just one person?
Can you guys?
Jonas, let's pause for a second. Give people a moment to just read the abstract and then we'll try to do the poll. So read for a moment.
All right.
Okay, I wonder if someone brave wants to raise your hand and give your view on whether this is or isn't mechanistic interpretability and why. Max,
okay.
Yeah, hi, can you hear me here?
Gotcha.
Nice. So based on what you said before, I did not think this was mechanistic interpretability, as this seems to be like a way to make your model perform better based on changing it, as well as I'm not sure, you sort of implied that you need to kind of have the whole, for lack of a better term, like reasoning chain within the neural network. And I did not see anything along those lines here.
This is a fantastic answer. Exactly. So I think your first cue is, as you said, the purpose of the explanation is to improve. And so that's different than, yes, here we go. Okay. So this is exactly, good job, Max. So in this case, the people who are doing the interpreting are like ML engineers trying to get a system that sort of works in practice, and they want better accuracy. And they're sort of looking at the model's weights on a given feature to try and adjust that. Let me just go back to this text. So let's see, sort of in the middle. Yeah, right in the middle. Explanation methods to increase the predictive accuracy. So that's the purpose of this kind of work. And then it's saying when the model has incorrectly assigned importance to some features. So it's sort of helping you find overweighted features, but it's not a complete chain of how that feature is getting weighted. So, right. So it's interpretability. I'm sure it helps a bunch of people and it's different than what we're talking about. Okay. So let's go back to here, what we're comparing. We want researchers getting a scholarly understanding and a complete mechanism. Here's another one. Let's try it. I'll give you time to read. Okay, anyone want to give this one a shot?
Yes, can you hear me?
Gotcha.
Yes, I think this is mechanistic interpretability, because we're trying to understand how the model is understanding like the curves. So we're trying to understand like how the model is doing with the curves.
Yes, exactly. Great. So that's the sort of the main thing, is that the kind of understanding we're coming up with right in the middle again. It's like, how are they built from earlier neurons? So it's a full explanation of their construction. I also added the second paragraph from the intro because it says the audience is the interpretability community, right? The audience is the researchers generating a scholarly understanding, and it highlights there's some disagreements in this scholarly community about how the network is built. So that's the couple cues you could use here to determine that this is researchers doing the understanding, communicating to other researchers, and investigating a full end-to-end mechanism. Great. So yes, the interpretability community, understanding how curves are detected and how neurons are built from other neurons. This is what we're talking about today. So I'm going to make a pitch for why I think this is a good place to start if you want to do independent research. So I'll first try and convince you that it's exciting. And one thing I'll say about this style of slides that I'm using, and I hope I'll be able to share them later, is I'm just going to link out to a bunch of stuff that's already out there on the web, in part to sort of empower you to look if you want to go deeper. The stuff that I'm presenting, most of it is already out there. So exciting stuff so far. I'm just going to plug the team that I've been working on. We post our work on this website, transformercircuits.pub. And we have a couple papers out where we're studying transformer language models. Quick show of hands, who here has a loose familiarity with large language models, generative language models?
10 people.
Yeah,
8
okay.
people.
So we've got about half. Great. Thank you, everyone. Yeah, so a little under half of folks. If you don't, I think you might find the details I'm talking about a little hard to follow. That's okay. I think you can listen for the sort of general principles of type of work that I'm talking about. So I'll be a little brief about cool stuff that we've found, but let me kind of just go thing by thing and explain like why I think each of these has been sort of exciting. So in this original paper that we came out with, this mathematical framework for transformer circuits, I'll just show you the contents on the side here. We've basically been able to reverse engineer 0, 1, and 2 layer transformers almost completely. So that was a lot of fun. And we have sort of mathematical concepts that we use to sort of explain and describe the different components of these tiny transformers that do generalize to larger transformers. So this was a big update for us, that it's sort of possible to get a handle on the full calculation within a tiny model. And then we sort of built up from there. So this is work that I've done, which, let's see, probably should have gone to the tweet threads rather than the paper itself for these. But so this work that I did, which was also incredible amounts of fun, was looking at this sudden, abrupt improvement early in transformer training in how well they can use early tokens to predict late tokens. And in fact, the very cool thing about this work is that there's this little bump that you can see. Anytime someone publishes a transformer loss curve, you can see this bump. It's amazing. Every single loss curve out there in the world has this little bump if it's training a transformer language model. So we just dove into like, what causes this? And at least in small models, we have a handle on exactly what is forming, which is a particular kind of attention head that causes this bump. Thank you, whoever posted that tweet thread. So this was a real delight, and sort of in a similar vein to that curve detectors paper, you can see in the table of contents over here, we have 6 different arguments of how we come to conclude that this mechanism is behind this observed behavior. There was a hand, I don't know if that went away, but put it back up if you want to ask something. So I found this very exciting to work on, where we can go all the way from a little bump in a loss curve to a complete mechanism of what kind of attention head is causing it. And then I'll just sort of briefly gesture at some other work we've been doing. These last 2 on the page are, how can we make the neurons correspond to concepts more cleanly? And so the softmax linear units is one change to models that we can make that seems to increase the amount of sort of distinct interpretable concepts on neurons. And then this toy model paper, everyone loves this paper for good reason. It's a delight, it's well explained, and it works on really tiny toy models. These are not giant transformers. You don't have to understand more than sort of a simple autoencoder to get through this. But we're sort of trying to understand, like, how and why is it that networks pack multiple features onto a neuron? Why isn't it always that you have the dog head neuron, the car wheel neuron? How come you sometimes have neurons that do dog heads and car wheels? What's up with that? This, I think, this toy model has given us a fantastic language and framework for thinking about that allows us to think more clearly about larger models as well. So this has also been very exciting. And I think overall, moving from the vision world to the language world, there have been a lot of new and exciting insights here as well. So that's just my quick pitch that exciting stuff is going on. And there's also a lot of low-hanging fruit, which I think makes this a particularly appealing area. So there's just barely explored stuff. I'm again going to go back to our group and point to our papers. But I think any of our papers, we have like an open questions section. And these are not, I think often, especially if you've like been sort of coached by an advisor how to write a paper, and they're like, put open questions here, and you just put like random crap that you don't care about. You're like, maybe someone could explore this in some other application, I guess. These open questions are not random crap. We really feel in our heart of hearts that like these questions, if someone made progress on them, would be real advances. So let me just start here. Like, is there a statistical test for catching superposition? I didn't define that because I'm going pretty quickly, but that's the phenomenon where it's packing two features like the car wheels and the dog heads into one neuron. We're like, can we catch that in an automated way? Right now, we just have to look at the neuron. If you could come up with a way that we could detect this automatically, that would be a game changer for us. You know, and there's other sort of questions like how realistic are these toy models? So you could take one of the toy models and then maybe a few layer transformer and do some kind of compare and contrast. That would also be incredibly valuable. How important are these neurons? If you can come up with some way of judging whether these sort of feature combined neurons are contributing more or less than the sort of simpler feature neurons, that would also be amazing. I'm not going to go through this whole list. It goes on and on and on. And all of our papers have a list like this, where, you know, the work that I'm showing here is from my team at Anthropic, which is just one small team, a small handful of people. And so we're trying to just go area by area, make a contribution, and then leave a lot of threads for people to follow. So I would love if people would follow up on these. Like I said, there's a lot of low-hanging fruit here. And then I think sort of the core point I want to make for this audience is that this work is approachable to generalists. Now, I'm very fortunate that my colleague Neil, who's currently an independent researcher in the UK, just put out a tweet thread about this. So I'll do a little compare and contrast where I'll show previous work. I'll explain sort of the tools you need, but I'm going to make use of this thread. He posted it just this morning, which saved me having to like add some more slides here. So I think, so Chris Ola, who's the manager of the team that I'm on at Anthropic, has put out a lot of great work on Distill in the past, especially on vision. My complaint is the past work is too fancy. I think it looks a little unapproachable. Now, it's a kind of an annoying complaint to have, because if you read a paper like this, The Building Blocks of Interpretability, I think it's a great explanatory tool, but it's like a textbook. You know, in a textbook, the images have been laid out as pedagogically crisply as possible, but there have been hours of work just into how to make that a teaching tool and sort of an enticing visualization. So you look like a graph like this, where they're sort of discovering like which channels are contributing to a different judgment. So then you can see like, oh, that dog eye channel, which is active on the dog eye, has sort of, you know, 1.19 net evidence for the dog class. And like, you can hover over this and sort of see, and it's a good learning experience. But if you're doing the work, you are not going to be working in this environment. This is not what your lab bench looks and feels like. This is the published product. So this might give you an impression that you need to be a data visualization expert. And in fact, if we look at the authors here, Sean Carter, who's a researcher I really admire, has worked on that paper we were just on. And oh, his past work is doing interactive graphics for the New York Times. This is like a top tier graphics expert. You do not need to be a top tier graphics expert, and your work is just as scientifically valid if it looks terrible. So here's a realistic experience of what working with these models is like. I can work in these sort of web interfaces that we've thrown together, where I just have different dimensions or different neurons, and I'm hovering over them and seeing where they activate and getting a feel for it. It is an interactive web visualization, but it's a much more approachable, down-to-earth context. And so I think what we do in mechanistic interpretability does involve building these interactive tools that we can use to understand, but they can be janky, and that still gets the job done. So I want to just make a pitch for, poor quality in terms of glossiness doesn't mean poor quality in terms of utility for getting your work done. As I said, Neil has this sort of guide for like, what does it take to get started? I think this is fantastic. I want to also just do a quick audience poll on some of these. So I'll just sort of skim through so you can see this is a short blog post. He's describing what skills do you need in order to contribute. So I'll read through the skills and then I'll do a quick poll where if you know one of these skills, then you can sort of sign up and say like, I would be happy to mentor, teach, explain other people in this community or other people on this call if they want help with the skills. We can do a little bit of peer connection. So I'll read through it. And then I think Jonas or Madeline is going to sort of run a little polling exercise. So yeah, Neil was like, people often get intimidated. Here's a guide to the essential skills. So the core skills that Neil's pointing out. So he thinks math-wise, linear algebra, you need to understand kind of what a basis is, and that a vector space doesn't necessarily have a canonical basis. If these words don't make sense to you yet, then there's a couple channels that can get you up to speed on this. Real basics of probability, it doesn't go very deep at all. Enough calculus to get what backprop is, nothing more. Coding, I think if you can just get Python and NumPy stuff working enough that you can then get kind of fast AI level machine learning, that's good enough. You really don't need to know how to like train really cutting edge models. In fact, I'm terrible at training models and I hate it. And yet somehow I've had a career in machine learning because mostly I analyze models that exist. So you don't need to be that good at training models. So long as you understand them as artifacts, you can do a good job. Yeah, PyTorch basically. And I think the current cutting edge that I work on is understanding transformer language models. So I think this is the section that might be most new, especially I saw maybe only half of hands went up for familiarity on this. I think there's some okay explanations of how transformers work. I think it is important to notice you can ignore the encoder versus decoder frame because modern transformers like GPT-2 are decoder only. So there is not this complicated double stack that everyone explains. So that's it. There we go. You know, there's bonus and then there's the end, but like this list is just not that long. So skills wise, I want to just sort of convey that in order to get started looking at neurons and understanding them mathematically, it doesn't take that much. Jonas, are you going to run this little polling exercise?
Yes, we can do that.
Great.
I wonder if the way to do this is to invite people to comment in the chat with their information if they'd be willing to share their skills with others. And also just an invitation to everyone on this call to join our community. And I think the Discord server that we're a part of would also be another wonderful place to connect with one another and share skills in this area.
Great, cool. So I'm just going to go skill by skill. Raise your hand if you feel comfortable with people asking questions of you about this. So let's just go with any of these math skills, linear algebra, probability, calculus. If you know any of these and feel like someone else on this call could reach out, raise your hand. Quick question from Max is what's SVD? That's the singular value decomposition here. Yeah. Okay, cool. So you have a handful of people who can answer maths questions. Amazing. Let's just jump through to coding, Python and NumPy. If you feel like you could help people with that, please raise your hand. Amazing. Let's do these first two machine learning bullets. So rough grounding in machine learning, PyTorch basics. I'll let hands toggle for a while. Amazing, wonderful set of hands. And then transformers. And I think because this one's a little unusual, especially if you are able to answer questions about transformers, please put your name in the chat or any contact details you're comfortable with. Okay, amazing. So yes, wonderful people on Discord. And I think this is recorded. So if you want to come back and look at that list of hands or otherwise understand who that was, that'd be great. So you have people in this community who can be a resource to you on this. You don't need to be contacting experts on the topic. So resources available. Amazing. Thank you, Max, and to everyone who's showing up with offers of help. So this is all to say that the set of prerequisites is just not that hard. And then I'll tweet out later today. I threw together this very poor quality tutorial about PySvelte, but better to release than nothing. So PySvelte is a library that we've released at Anthropic. I'll just click through to the GitHub, which allows you to sort of move your data between Python and JavaScript. So I'll just highlight this one paragraph that explains basically what it is. You know, the vast majority of deep learning research is done in Python. There's sophisticated libraries. Great. However, if you want to visualize stuff, these web standards, HTML, JavaScript, CSS, are sort of the right library for putting things on a page, having clickable buttons, and so on. So how do we deal with this? We don't want to try to use JavaScript to train models. And I think for interactive clickable visualizations, Python is a bit of a tricky place to do that. So what do? We attempt to bridge the ecosystems. So we have this library that allows you to take your data in Python, throw it over to an HTML web page. Svelte is a library like React, but much simpler to use, that you can use this library to get your data from Python to a visualization like that. So I won't go into too much more detail about this, but I'll just sort of release it and say, if you want to learn how to use this library in order to get interactive visualizations of your own running, I will release this little tutorial. The library is already out there on GitHub. Okay, so here's sort of another realistic example of someone's workflow. Again, Neil has been tweeting up a storm. I'm very grateful because it makes my job easier. Neil says, I've been learning basic web dev recently. I've been pleasantly surprised by how useful being able to make hacky interactive visualizations is for mechanistic interpretability. Here's a shitty tool I hacked together on how to explore a GPT-2 neuron that activates on text. I'll just let you watch this animation for a second. So he's made this text box where he can type, and then it's clearly polling in the background a server where it's getting activations from GPT-2, a pretty small model, and then coloring the tokens by their activation on this particular neuron. So he's doing kind of a deep dive on a specific neuron, what it activates in response to, how it behaves, and he's just handwritten this little tool for himself. So what I want you to take away from this is that these are simple JavaScript components, text boxes, colors, background colors. You do need to know a little bit of HTML and CSS to do this. It's just not that much. And it doesn't need to be as beautiful as a distilled paper. Sorry, I've got a bunch of sunlight on my face. Adjust that. So yes, this is not as beautiful as a distilled paper. It's perfectly usable. I think this is very approachable stuff. And so I'm grateful to Neil as my colleague for banging the drum on approachable tools for doing this kind of work. So bumping back over here, one question you also might have is like, okay, that's skills, that's tools. What about compute? How many GPUs do I need to do this work? So I want to just bump us over to this work that I did. Oh, that's interesting. I mistyped something. Let's figure that out. Here we go. Okay. So this is work I did that to do this work took a lot of GPUs, but any given model that I'm studying is quite small. So let me go to these sort of ablation studies, right? This is very GPU heavy, where each of these lines is a model that I've trained, and I've measured something about it at like every single step of training, and I've ablated heads. Like each of these is a single model, right? So I've gone kind of over and over again with lots and lots of different models. So this kind of like multi-scan ablation work is going to take a large number of GPUs, but you don't have to do work like this. So one thing I mentioned is like, look at this. This is like a single 1-layer and 2-layer model. You could build this kind of visualization if you had just a single GPU on Colab available to you. You could train a 1 or 2-layer transformer with no problem. So even in this sort of large behemoth of a paper where I did scan after scan and sweep after sweep, I was just filling our cluster with truly hundreds and thousands of tiny transformers. But any given tiny transformer you can run on one GPU, and you can inspect these neurons and these properties. I'll also say the toy model work. These toy models are even smaller in some cases, and also can be done with very minimal resources. Another thing is just anything that runs on a GPU, you can study. So you don't necessarily need to pay the resources to train the thing, right? I was just showing you that both the toy models work and the induction heads work are helpful if you can train over several time steps your own tiny model. But you can also study already trained models, and then you just need the ability to run at inference time a language model, which is much cheaper because you don't need to spin it up and teach it everything it doesn't know. So for inference time work, any model where you can access the neurons and access their activations is enough that you can start studying it. So that's another pitch that I want to make here. Okay, so compute-wise, I think there's plenty of questions that are accessible with a small amount of compute. This is another reason I'm really trying to pitch this group on this kind of work. So a couple difficulties if you're starting on this kind of work as an independent researcher, as I say here, 4 and 5. There's gotchas. So there's stuff that might seem mathematically intriguing or intuitive to jump into, and turns out to actually be like kind of a confused or not well-founded way to think about it. Sorry, I'm still a little distracted by all these light beams streaming at me. Okay, there we go. So this can be tricky. And I think if you're doing work like this, it's helpful to start getting feedback early so you avoid this kind of thing. So here's one gotcha. We talk about studying neurons. Okay, here I just cropped out a little chunk of the illustrated transformer. And you might ask, like, where here are there neurons I can study? And so we do study in these sort of the boxes labeled feed forward. That's where you have what we conventionally call neurons. These are, vectors where each entry of the vector then has a nonlinearity after it. It's like it has a firing function or an activation function. And those are sort of entry by entry in the vector, has its own activation function. And that's why you can study each entry one at a time, because they're independently operated on and they have what we call a privileged basis. So that's why we study neurons in these feed-forward layers. Now we've had people approach us and say, why don't you study neurons in the residual stream? This is kind of a poor diagram of it. I'm sorry I couldn't draw a better one. You can see these dashed lines that are kind of circling around. I think a transformer is often well thought of as just there's kind of this residual stream that's constantly flowing through. People are like, why don't you study those dimensions? And the first objection would be like, it's not a privileged basis. It's just a big vector. The elements of the vector don't individually mean anything. So why? So that's kind of the first, so first pass, no. And I've just dropped this link here where we explain in one of our papers what is a privileged basis. I'll just read this out. So a privileged basis occurs when some aspect of a modeled architecture encourages the neural network features to align with the basis dimensions, the individual entries of the vector. For example, blah, blah, blah. Some type of interpretability only makes sense for activations with a privileged basis. It doesn't make sense to look at the neurons in the residual stream. Okay, so this is sort of a first pass where people ask us this and we're like, no, it doesn't make sense. Okay, it gets more complicated. Okay, so actually, sorry, before I say it gets more complicated, I just wanted to throw this diagram in here where this is just a two-dimensional vector space. And these are two different features. Maybe it's like the cat feature and the dog feature or something. And these features are represented as vectors. They're orthogonal vectors, but they don't line up with like the X coordinate and the Y coordinate. So this is what I mean when I'm saying like doesn't line up with the basis vectors. Okay, so again, thank you, Neil, for tweeting all this stuff, which makes it very easy for me to show off. Then there's this question of like, but maybe there is a basis, a privileged basis in the residual stream because of the way floating point arithmetic works. And so I've linked, there's sort of this post that he links out to and this other question. And like, you might start working on this and be like, is there or isn't there a privileged basis in the residual stream? And I just want to stop here and be like, this is sort of the cutting edge of our understanding of like whether you can or can't think of those neurons as meaningful. And if you can, it's not because of the math of the transformer, it's because of leaky abstractions. And so I just want to back out and be like, okay, there's gotchas here. This is complicated. And if you want to do work that is mathematically well-grounded, it can be a little tricky to make sure that the concepts you're thinking of, that you have your ideas perfectly clear and crisp. And so if you want to work on this kind of stuff, I suggest tweeting about it or writing little one-pagers of your understanding and showing them around and getting people to look over it and say, like, am I thinking about this right? Here's a few paragraphs of my thinking, getting people to check you. Don't go months and weeks and months down a rabbit hole of some research idea before you check with other people in your community that you are thinking clearly about it and that your concepts, you have the right assumptions about the basic concepts you're using. So that's gotchas. The other concern you might have is just, is this stuff legible as normal research? You know, if you're trying to build legible credibility, the kind you'd get with a machine learning PhD. I think there are pros and cons of trying to do that with this work. So you might ask, well, what can I publish if I do this kind of work? So there's formats, right? Archive papers, plenty of folks have published archive papers on mechanistic interpretability. There's now a long history of interactive websites, which I think are a fantastic way, even if they're a little janky, to sort of get people's hands on the stuff that you found. There's a lot of Twitter threads. Again, Neil just published some of like, here's a cool thing that I found. There's not a lot of like journal and conference published work out of this community. Okay, why is that? Here's why. So the kind of findings range from, I found a cool neuron, and let me just put a gold star on this and be like, this is a wonderful finding. If you just find a cool neuron, it's the equivalent of like being a biologist and you walk out in the field and you're like, I found this bug that might be a different species. It's not the same as like a full field survey to fully characterize the new species and prove that it's a new species, but it's a great starting point. It's vital. And so if we had more folks who were just looking through neurons and models and being like, what is this? This is like an alphabetized list neuron. And then you throw that on your blog or you tweet that. I mean, tag me if you do. I love this. It's wonderful. It's a meaningful, real scientific contribution. It's something people can follow up with to confirm. Okay. But I found a cool neuron is not going to get you published in Neurips. I'm so sorry. So there's just like the scale and scope of what is like an entire paper-worthy contribution is larger than the scale and scope of what I would find cool to read on your blog or Twitter and what I would love to see. And then they're sort of getting into like, here's an explanation of a mechanism. Here's how a curve detector works. Here's how induction heads work. Here's what they do. There's no state of the art on anything. Even if you write like, you know, long textbook chapter like explanation of the mechanism you found, I think it's a little unclear as to which conferences and which reviewers will understand this as a contribution if they are used to seeing contributions. It's like, here's my new technique and here's how the numbers went up. Or here's some performance evaluation. These don't come with performance evaluation. And so I think it's a little unclear which reviewers are going to find that in scope or be able to understand it. So that's part of why this community has been developing somewhat outside of conventional conferences and academia, for better or for worse. And, you know, I've been glad to see more people submitting archive papers, which at least starts to get things in a format that then could be submitted to journals and conferences. But I just, you know, I want to like pose a real warning that for all that it's great and approachable, that just finding cool neurons is valid research contributions, it also might not give you something with the stamp of approval that you're looking for from the conventional authorities. Although I will just reassert that getting a community of your peers to look at what you're doing is very important. So even though I'm describing, you know, interactive websites, Twitter threads, let me see if I can just bump over. We do get all of our stuff pre-publication peer reviewed. If you go to the bottom of any of our papers, sorry, it's a long paper. We put at the bottom comments and replications that we've solicited from our research community. So we send it out to folks, we get comments in, and we get people to replicate our key findings just to make sure that we are confident in what we're putting out before we put it out there. This step is really important. And, you know, when you put out a blog post or something like this, it's important to sort of say, here's what I did, here's who I had look at it, put in your acknowledgements who looked at it, solicit any comments that you can, put it out there in a space where people can chime in. I think this sort of scholarly community discussion and validation is important. So even if we're not doing this through a a publication venue that's then assigning us 3 different reviewers and scores. We are nonetheless getting this reviewed by peers. I think that's key. And especially if you're an independent researcher, finding your other channels to get feedback is really important. So yeah, and you can also check out, I think many of these replications come with their own code, or they might be accessible on publicly available models. So if you want to take as a jumping off point some of our work, this can be a good starting point. So let's see, I think I'm pretty much done. I just want to kind of review overall where we've come. So I hope I've convinced you what this field is, that it's exciting, that there's a lot left to do, genuine open questions. The skills needed are approachable for folks with a basic technical background. There are gotchas, and there's this legibility problem where it's maybe tricky to get a published paper that's in a format other people would expect. I think nonetheless, there's like a growing community, many of whom are on Twitter, who are happy to chime in and support you. So if that's appealing to you, I think the approachability and the excitement is a good selling point as well. So that's me on getting started in mechanistic interpretability. Thanks for showing up.
Awesome. If you have any question, you can put it in the Q&A. Currently, I don't see any question, but I was just wondering, earlier on, you showed that there are some open questions that if someone wanted to, let's say, address any of them, what's the best way for them to reach out about those questions?
Great. Yeah. Feel free to email me. I can just drop, if I put in the chat here, is that going to work? I'm Catherio@anthropic.com. I will try and find whoever on our team is best posed to help you out. Although I'll say we're busy. So probably you might just get one back and forth from us with a quick pointer. You probably will not get like an extended mentorship relationship, but we are happy to point you to resources or people. This is part of why I suggested trying to get mentorship from the individual sub-skills that are part of this. So if you're having trouble building a visualization, find someone who knows JavaScript. You don't need someone who's an expert in these particular questions. And then I would suggest once you have kind of early findings or kind of direction you're going, I think Twitter is a fantastic place to go, where there's enough people out there who are then able to sort of read through what you're saying. I think also if you have, blogs or newsletters, those kind of things work well, although you don't need to have that. But I would suggest, yes, Twitter is a great sort of constantly open community forum. Yeah, I mean, and again, like if you have even just a one-pager with your findings, if you have done a rigorous analysis, even if it's very small scale, and you're confident in your findings, I think putting one-pagers on archive is undervalued. It doesn't need to be like conference type to be a valid contribution. So I think consider also putting your one-pagers on archive. Like I said, if they are rigorous and you feel confident in them, I think that's a good thing to do as well.
Right. Yes, that's fantastic. If you have a question, you can just raise your hand. Maybe I can also ask for now.
And
Let's give people a moment. Let's see if something comes up.
Yeah,
Yeah, so
we have 2 new questions in the Q&A.
Oh, yeah.
Jonas, are you able to pull those up?
All right.
I've got these. Okay, so let's see. Okay, I've got one. So from Sri, how domain agnostic is the research being done in this space? Has there been any work done in this direction to transform exposed to vision and maybe audio? I don't know of any mechanistic interpretability work on transformers not for text. Just none yet. So speaking of low-hanging fruit, I think if you were to find any basic transformer on vision and audio, and just see, does it even have induction heads? I think that would be a fantastic and very approachable question. Okay, Max, my intuition is that adding vectors such as after an attention softmax layer loses information and hence wouldn't be super interpretable. Is this intuition that adding is worse than multiplying matrices correct, or am I on the wrong track? Max, can you just chime in verbally? Because I'm not understanding how adding vectors loses information, and maybe we can get a little higher bandwidth here.
Sure. Hey, So my
Hey.
intuition is that, combining magnitudes of vectors kind of
Yeah.
just sticks you in some area of the whole embedding space, as opposed to sort of, more gracefully combining them. And I'm also, when you compute gradients through things, it makes more sense in my mind when you sort of are multiplying them to see those gradients flow backwards. So, so those are my questions. It's like, wait, wouldn't adding vectors then lose you a lot of stuff? And thus, specifically, I felt like it would be related to this interpretability, where if you kind of add them together, you would also kind of lose some backprop. But again, I'm not quite sure if this is a correctly posed question at all. So
Yeah, I think I'm going to try to answer you both impressionistically and literally and see if that'll land for you.
Great.
So, literally, right, the intention is so if you just have some pile of vectors, then you add some other pile of vectors, like you, in some sense, you're right, you have lost information, but it's sort of like, you haven't necessarily deleted the magnitude on the original direction. You sort of then just like contributed additionally another direction. So it might be hard to then decompose, like, if those were not orthogonal, what fraction
Sure.
of one or the other. So I think theoretically, like that's true. You've sort of lost like a truly unique decomposition that you could back out. That's going to be true, of course, anytime you have nonlinearities. So all of your neural network is full of places where you're just losing information in some sense. I think in practice, it seems like often the residual stream keeps what was already there and then piles on additional stuff. So if the projection along the vectors that were kind of already present largely remains present, and then other projections also are added. Although impressionistically, it seems like some layers are doing something like deliberately removing or deliberately deleting information. That makes sense because there's in a transformer, right? Each layer is moving from more like sensing and interpreting the original context so far through to outputting the next token, right? And so as that representation transforms, it needs to become more and more narrow towards what do I say next? What's the next output? And I think that narrowing is necessarily through the layers going to drop information that's not action relevant for the transformer.
Yeah, that makes sense.
You can analyze it at different layers and then see how does this representation evolve. We do have, again, I'm like the expert on the induction heads paper because I was pushing that one forward. And we do have a sort of analysis of how do induction heads form, like in what layers do they form? And it is kind of these middle layers where it's doing these sort of more complicated things. And those kinds of heads are not present towards the end. I think remains to be seen. It could be a fun little analysis to be like, the representation output by the previous token head or the induction head, does it get deleted by the end or does it just sit there? It just doesn't matter. I think these are interesting questions as to, in practice, does the information get deleted? Yeah, I think that's kind of pragmatically an open question.
Nice. Thank you so much. Yeah. What exactly information? It makes a lot of sense to me that like you have something that you end up computing an error on that you gradient backwards through. So, eventually you need to kind of narrow down towards that idea, and things will you'll lose information. Thank you so much.
Yeah, of course. More questions, please. These are good ones. Okay, here's what I've got. Is interpretability of high dimensional data possible, considering that we only understand 4 total dimensions? I think you mean like 3 dimensions in time. Wonderful, wonderful question. So there's 2 things we can do to get a handle on high dimensional data. One is, as I've repeated over and over, and I won't dwell on, if you have a privileged basis such that if you have 300 dimensions, you think the individual dimensions matter, you can just with your eyeballs go dimension by dimension. This works in small to medium sized transformers. In a small transformer, I can and have just look at every attention head and perhaps even every neuron. That will run out once you have a 60-layer transformer with 30,000 neurons per layer. That's going to stop working. So then what do you do? So yeah, I guess all that to say, something like 56 dimensions is still tractable if there are privileged bases, because you can look at them one at a time. If you have more than that, or it's not a privileged basis, then you need some other approach. That's almost always going to be dimensionality reduction. I think until you've tried it, don't rule out that a regular PCA, or honestly, we often use NMF, which is a non-negative matrix factorization. A basic PCA or NMF can easily give you broadly what's going on in this vector space. Other things that are helpful is a UMAP. So let me just type these. I was saying a PCA, NMF, and UMAP. These are built in scikit-learn. You don't need to write them yourself. There are tools to do it. If you have a bunch of vectors in a vector space and you want to see roughly how they are clustering, I think a UMAP is a good way to do that. These can just get you basically oriented, but I think if you want to go further, you need a little bit of mathematical rigor to then pose what question you're trying to ask, and see how you can thread that question through a high dimensional space and get an answer.
There's another question.
Yes, let's do it.
Yes.
Great. Haley's the last question. Thanks, Haley. Okay, I'm curious what intuitions you have on bridging the gap between toy models, toy data settings, and realistic sized LLMs trained on scraped data. How would you advise applying theories or characteristics you've seen in small models to large ones to see if your analyses hold? Especially curious how to think of the layer norm here for large transformers. Okay. Layer norm sucks. I'll come back to that. How? So I think the best we've done is if you look at the induction heads paper, we sort of say we've done a rigorous analysis on the small transformers, and we have suggestive evidence of how it scales up to large transformers. I think that's going to be the paradigm for a little while, at least, where you have statistical correlations that seem to line up. But you can say this thing that we can basically prove is going on in the small transformers looks similar, looks roughly the same. There's, I think, always going to be some of that gap, but I think as we see more work like this, and I would love to see more work similar to that induction heads paper that's doing those correlational and suggestive analyses of why it holds, I think we'll get a better handle on, do those seem to hold? And there's always some gap. So again, I'm going to point you back to the induction heads paper where I've spent the most time on this. We do say our main hypothesis is that the driver in the small models was the induction heads, and we think that's true in the large models. But it could also be there's other things with the same properties, other sort of Q, K, and V decomposition. We can't rule that out. So I think as you bridge that gap, you're going to end up with these little annotations. It's like, we can't rule out that something else is going on. And I think the march of science involves leaving and then slowly eating away at those unanswered questions. Okay, layer norm sucks. We've put in a bunch of effort to try and train models without layer norm. If you would like to throw yourself against the brick wall of that problem, by all means, go for it. I think we're running out of time, but yes, your intuition is right that layer norm makes a lot of these analyses more challenging. That's it. Thanks, Haley.
Catherine, thank you so much. What an engaging and thorough introduction to mechanistic interpretability. Wow, I think we're all walking away with lots to look into, lots to read, and lots of research to do. Let's get to it, people.
Get on it.
Thanks to Jen and Jonas once again for organizing and coordinating this session, and to all of you for coming. If you'd like to learn more about Cohere for AI, you can find us at cohere.for.ai. Thanks so much, everyone, and have a wonderful rest of your day.
Thanks for showing up. It's been great.